that you have t, this is t equals to 2, so j was always greater than minus 2. If t is minus 2, that's not always the case. Exactly similar result. Here's the Schur functions in non-standard form. This is the standard one, 0, 2, 1, 3, 1, 3, 0, 2. And you see that there are only two hooks, if you like, AR plus BR plus 1, for which this differs by 2, 0 and 2 and 1, 3. Why don't we have 2, 5? Well, because I'm working in n equals 4. And that would make the length too long, and the Schur function would vanish. So that's it. Now we can prove the conjecture. We started with McDonald's formula. We then rewrote it. This is the conjugate length of the conjugate, the length of the row is less than equal to p. And that's McDonald's formula. Rewritten. And now we can use the lemma when q is minus 1 and t is p, and we can transform that to a statement in terms of Schur functions. If we wish, and this result was obtained simultaneously, just about the same time, 2008, by Popov and Professor Lowy. They obtained this result. So that's not new, but they obtained it in a different way. Then if you manipulate these using the Littlewood formula, you can rewrite it in terms of ratios of sequences of Schur functions, sine sequences of Schur functions, and you can write it in yet another form. The importance of writing it this way is that you're now in a domain in which everything is expressed entirely in terms of Schur functions, and you're working within this ring. Actually, the ring is extended to include infinite sums of Schur functions, but the ring of symmetric functions in which there exists an important conjugacy relation, which I want to exploit. There's this automorphism on this ring of symmetric function, which is just conjugacy. So it maps S lambda of x to S lambda prime of x. But that doesn't change the weight of the partition, nor its Frobenius rank, but it changes the set in which the lambda sits. It may, if we have a lambda that sits inside this set Qt, then lambda prime, because it interchanges rows and columns, makes certain that lambda prime sits inside T of minus T. And so you can check that all those things are true. And the factor that we had in the exponent, this factor is invariant under this transformation. And that's to say f lambda of p changes to f lambda prime of p. You can check that. So we're ready. We use the conjugacy result. We take now a set of Schur functions restricted in column length. The length of lambda is less than equal to p. That's the conjugate of the left-hand side. We conjugate both of the others. We arrive at this. We can now use Littlewood backwards, and we get for this denominator. Well, I put it in the numerator. You can transform that to this denominator expression, and then you can rewrite this using the Littlewood identity, or special case, if you like, of what's gone before, or the Popov-Lowy result, and you get the L-speed conjecture. So that's completed the proof. As a bonus, you get another determinantal form, like McDonald's, appropriate to this sum over Schur function. The big difference between this formula and the McDonald's one is this is infinite. These expressions are all infinite sequences of Schur functions, whereas this is finite. That's the big difference that we have. Okay, so I could end there. We proved this conjecture, which is bugging a bit, and I couldn't see how to proceed. But it doesn't explain anything. It just pops out somehow. So we've recast the numerator, sine sum, we've given these conjugacies. We've not explained why these determinant expressions lead to row and column length restrictions. And we can, in fact, give some sort of explanation because of the connection with characters. I haven't used any connection with characters. All I've just combinatorics for Schur. And then we look at alternative ways of evaluating these characters. Okay. These are the classical group characters, all written in terms of determinants. Do you see McDonald's one there? Well, not immediately, but it is. You stare at these and you think, well, it doesn't look quite the same, but it is. And this goes back to a theorem that originated in Bracken and Green in 1972. They gave an argument for this result, that this sum over Schur functions restricted by the length of lambda prime, being less than equal to p, is this form times this character, which we've just seen, but didn't recognize, of the orthogonal group in an odd dimensional space. with highest weight P over 2 to the power n. That reminds me of you a bit, I hope, of what Doris was saying earlier about some highest weight representation. So it's been discovered many times, and the McDonald's is slightly unusual. This is an exercise, it comes in McDonald's book, but you have, I was speaking in section 2, but you have to read section 3 and understand it before you can prove this. It's kind of hard proof. Arcada's proof is more direct, and it's the simplest to follow. Okay, so now we can use McDonald's theorem and rewrite its determinants in terms of these characters. And this is McDonald's theorem. You just take out, this is one way of writing it, you just take out some common factors from each row and for each column, you cancel these fellows and you're left with xi to the p over 2, which is this thing, and the thing you've got left is this character. Just look it up, it's that character. So we have a connection. How much time do I have? Okay, let's see how much I can say. I want to use the notion of dual pairs of groups to get information on these characters. So let G and H act on a linear vector space. They mutually centralize one another. It's not just commuting. And as a representation on this module, as a representation of G cross H, let V split up in this way, in which K varies over some index set, and lambda K and mu K are irreducible representations of G and H uniquely determined by K. It doesn't matter what the formula is for going from K to lambda and mu. But they vary without repetition. So this is a characteristic property of this structure. In such a case, we say G and H form a Howe dual pair with respect to T. So this is what's playing a role in this, these relationships we've had before. Well, let me just flash it up and go quickly. We've all seen examples of this in action, and one of the consequences, if you act on this symmetric space, polynomials n, Cn cross Cm, in terms of characters, we have the Cauchy identity. If you do it on the exterior cards, you get the dual Cauchy identity at the level of characters. So those are examples of a Howe dual pair situation acting in practice, and these are well known in the combinatorial world involving the Schur function. Notice the length of lambda is restricted here to the minimum of the number of letters in the alphabet X and the number of letters in the alphabet Y. Here, lambda has to be a partition which sits inside a box in which the first part of lambda cannot be bigger than n, and the first column of lambda cannot be bigger than n. There's a dual relationship. If you're lucky, V is an irreducible representation of some group, and on restrictions of the subgroup, we get this character identity that follows from the Howe dual pair relationship. And amongst the set of such dual pair situations, we have all of these. And there's a whole tribe of people who've identified these and work with them. The point is they give you some interesting results on the characters. I didn't have to say a word about notation. If I've got a partition lambda, its reverse is just, oh, that's lambda 1, that's all. You write it backwards, you subtract it from Mn, you get this object. If lambda is a partition, then so is this a partition, as long as M is greater than or equal to lambda 1. I call half to the n delta. Delta lambda is this object, delta mn lambda is this object, and to go from lambda to mn minus lambda, you turn the diagram upside down, put it in the box and throw it away, and you get mn lambda. Okay, well the theorem is this. If you look at the spin modules of these large groups and restrict them to these pair of subgroups, you get these identities. And two of these we need, this one and this one. These two identities both involve the orthogonal group in an even and odd dimensional space, but here an orthogonal group in an odd dimensional space. And we have restrictions on both length and breadth of this partition in those sides. And that's the origin of these restrictions on length and parts of partitions. And why are dual pairs useful? If you have a formula of this type, you expand it. If you don't know anything about this character, you can work out things about the character because it will be the coefficient of this partner. So if you can pick out this partner, you'll be able to evaluate this character. That's what you do. You work from the left, you evaluate that, you pick out the coefficients of these, which you seem to know, and that will give you information on these. Okay. And all you need for these spin character identities is the dual Cauchy formula, classical group characters and some modifications. So here we go. If you look at this dual pair, we have this identity as a result of the Howell correspondence. If you don't go through a conventional branching down all this chain, O2, NP to ON2, these are all well-known classical branching rules. You know how to do all of those. You get this result, and you can see that if you compare these, if eta prime and lambda prime are the same, it looks as if you've got a formula for this fellow in terms of these fellows. And you have, but you have to be a little bit careful, because this sum over eta prime extends further than this one, or the other way around. Yes, that way around. So you have to compare these coefficients carefully. If you do that, if you set lambda equals naught, which is the case we're interested in, to the n, you get this result. You now sum over those etas such that this object is the same as this with a 0 here. In this case, you're lucky. There's only one term. And this is the answer. And this is Bracken and Green's result. I was annoyed. Very annoying. I couldn't prove this result until I knew about how to compare it. And had lots of other ways of calculating it, but not the general result. Okay, well you do, that's the Bracken and Green result for you. Okay, that's precisely McDonald's. We'd want to do the same thing for the Joris conjecture. And here goes. This time, we look at the metaplectic representation, the biorepresentation of the symplectic group. And this is, I give it notation for me, so I call it delta quibble. There are dual pairs. Here are the dual pairs in this situation, well known since the time of Howell. But we want to exploit them, and there's some theorems, one version of which I was involved with, which enables you to calculate these characters. And this gives these results, a collection of results on the characters. From those, the dual pair decomposition gives you this fellow, and this is not quite what Joris is interested in, because this is the symplectic group, not the orthosymplectic group. But it's close to it. And we're interested, in fact, in the special case where this lambda reverse is a sequence of ones. But you can read off from this expansion and this a formula for these. That's the important thing. So here goes. Setting lambdas 1 to the k, we do it, blah, blah, blah. Look at the restriction. There's no modification warriors in this case. And we get this formula here for this character with 1 to the k in here. But this is not Joris. This is the symplectic, not the orthosymplectic. But he told us how to branch from the orthosymplectic. So we can then use that and sum up a collection of these for all k, which we haven't summed before. Oops, what have I done? Oh yes, here we go. This is the origin, blah, blah, blah. We have to sum from k is 0 to p, he tells us, to get these characters. And here they are. We do the summation. This 2 psi means all the parts of the partition are even. You multiply by a partition in which all the parts are just 1, and you can get every partition, and you get every partition once and once only. But the length is restricted to be less than equal to 0. So that's it. So that's a somehow rediscovering this result using dual pairs, but in some sense explaining where these restrictions on row and column lengths come from. And I'll probably say everything I want to do about the conclusion. There's a superalgebra way of doing this due to chain quantum Wang, where you can work directly with a dual pair, with one of which is super. And that's really what I should have done. And that's a neater way of getting to the same result. But the method is exactly the same. There's no difference in the method. It's just that we're talking about orthosymplectic algebra directly. So thanks, Tchavdar, for your inspiration, encouragement, and friendship. And belated congratulations on your graduation. Thank you.